The next section in our unit of solutions is molarity, which has to do with the concentration of solutions. But before we get into that, I wanted to make sure that we had the difference between the dissolution of ionic compounds and covalent compounds. So we've tried to explain and we've tried to draw different pictures of the water molecule taking apart ionic solids. So if you imagine this as being a grain of salt, the water molecules are going to orient, or they're going to place themselves in a position where the partially negative parts, those oxygens, are going to be facing the cation, which is positively charged, and opposite charges attract. So if you get enough of these water molecules oriented in the right way, they can pull those cations off. The hydrogen ions are on the side that is partially positive, so they are attracted to the anion, which would be chloride in this example. And so you have all of these ions that are being separated. So this grain of salt here has all of these millions of atoms with charges that are being pulled apart. The atoms are literally being pulled apart. So the difference when we're looking at something like sugar is that we're not going to have the atoms being pulled apart from each other. And remember that the reason why these are being pulled apart is that water is a polar molecule. And I want to remind you that we've got a partially negative side with oxygen that is very electronegative. We have a partially positive side on the hydrogens because they are weak. They have a very weak electronegativity, which means that they do not get to hold on to those electrons very well. And then also, there are things called covalent bonds and hydrogen bonds, and they are not the same thing. So, for example, if we are looking at this hydrogen molecule or this water molecule right here, we would see that there's a bond between each of the hydrogens and the oxygen, right? So that bond right there, that is a covalent bond. And that is different from the attraction felt by this hydrogen towards this very electronegative oxygen over here. So these are oppositely charged, and they are attracted to each other because of that difference in charge. That is your hydrogen bond. And that's something that we're still getting confused. But it is this polarity, this positive pole on one side of water and negative pole on the other side of water, that allows it to dissolve different substances. And so we saw how the water molecules will surround the cations and anions in a salt. Well, they will do something similar to something such as sugar. So this is sugar here. It is not ionic. It is completely covalent. It is made up of only nonmetals. It will look like a solid structure, crystalline, just similar to salt. But when these come apart, they are not going to come apart as atoms. So these are all sugar molecules right here. So each one of these, the solid would be stuck together, very compact, because that's what a solid is. But it's C6H12O6. So there's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Those are oxygen. There's one hidden back there, 6. And then if we counted all of the hydrogens around, there would be 12, but some of them are hidden on the back. So what does water do? Well, water has a positive end that will surround these negative ends, and it will want to pull that away, pull it away from the rest of the solid molecules that are there. And so let's see, this one will turn around, and it will attract these, and it's the surrounding of the molecules that's going to move them away. So the water is going to do that. But notice that in all of these, the sugar molecule is intact. These individual atoms are not separating from each other. They are intact. And so that's the difference in how we dissolve a covalent compound versus how an ionic compound dissolves, which is what this was up here. Okay, so it's going to be time to stop the video. Let me just go through this and then you can write down the definitions. So what we're looking at is a review, a reminder that a solution consists of a liquid, which is a solvent, and the solute, which is dissolved in it. You're familiar with some solutions, such as milk, which has lactose, salts, and fat in it. Ocean water is another type of solution. They are known as aqueous because the solvent is water, and that's what most of our solutions that we encounter are going to be. The amount of solute in a solution is known as the solution's concentration. And there are different ways to measure concentration. We actually did a lab with percent earlier, but we're going to be focusing on molarity. That's the most common type of concentration that we're going to deal with. And so here's the formula. Molarity, capital M, equals moles of solute divided by total volume of solution. So go ahead and pause the video, write those definitions down in that formula, and then we'll get started on using that molarity. I'm going to write down the formula for molarity, and for each of your calculation problems, you should do the same. This is going to be an easy formula for us to manipulate when we are solving for our variable, our unknown variable, but we still need to make sure that we're writing it down and showing all of our work. So as an example, I have here 2 beakers, and in each beaker I have 14 particles that I am modeling with these dots here, 14 particles. And I'm going to pretend, let's just say that this here is a 1-liter beaker, and that this is a 2-liter beaker. So if I pretend that each of these dots represents 1 mole of particles, then I can say that the molarity of beaker 1 is, let's see, what did I say, 14 particles. So I'll just pretend 14 particles equals 14 moles for this example. And it's in a 1-liter container. Well, so that means that we have a 14 molar concentration solution. And so the capital M, and it does have to be a capital M, that is referred to as molar, or we will also say that this is the molarity of the solution that we are calculating. And so what if I have the exact same number of particles, 14, but I now have a 2-liter container? Well, let's see. Molarity equals number of moles divided by, this is a 2-liter amount of solution. 14 divided by 2 is 7. So this would be a 7 molar solution. That would be its concentration. And that's it. That's what molarity is. So let's do some practice. I'm going to start some practice problems here with us. Let's start with this number 1. What is the molarity of a 0.30 liter solution containing 0.5 moles of sodium chloride? So the first thing that I need to do is I need to write my formula. We are dealing with molarity. There's my formula. I need to write what I know and what I don't know. They're asking me for molarity, which is great because I don't have to rearrange my equation. It's already set up to find my unknown molarity. So that's my question mark. That's what I don't know yet. I do know 0.30 liters. That's the volume. So I can write that the volume is 0.30 liters. I know that my number of moles, also given in the problem, is 0.50 moles. And we're talking about NaCl, sodium chloride. So I can just plug that in. And this is going to be 0.50 moles of sodium chloride divided by 0.30 liters. Each of those numbers has 2 significant figures. So plug that into your calculators. Pause the video. Plug it into your calculators. To 2 significant figures, I get 1.7 molar sodium chloride. Right, so 1.7 molar. And because we are dealing with different substances and chemical reactions, we need to make sure that we specify which chemical we just calculated the molarity of. That was sodium chloride. All right, so another one. Let's go ahead and do number 2. Number 2 is also asking for molarity, which is nice because it means that I don't have to rearrange my equation. I'm going to write down what I'm being asked for, molarity, and then I'm going to write down what I do know. I do know that I have, for moles, I have 0.289 moles of iron 3 chloride. Iron 3 chloride. And they give me a volume. Ooh, but they give it to me in milliliters. So really the biggest thing that you're going to need to make sure that you watch is that you have the same units. We have liters in your formula, so that has to be in liters also. So what that means is that I need to do a conversion, but that's okay. We can do this. In order to convert from milliliters, I want to cancel out that unit, so I copy it diagonally. I want liters, so that unit goes on top. And then I put a relationship between the two. Well, it takes 1,000 milliliters to equal 1 liter. And now I can multiply across the top, divide by what's on the bottom. Milliliters over milliliters cancel. And so I end up with 0.12 liters of solution. So now I can go back and plug all that in. So I'm going to write this down. Pause the video and check your answer. Let's see, what I get is 2.4 molar, and I have to say which substance I'm working with here. It's iron 3 chloride. All right, that's it. Ready for another one? Ready or not, let's go on to the next one. I'm going to do number 6 next here on these examples. How many liters of solution are needed to make a 1.66 molar solution containing 2.11 moles of potassium permanganate? All right, so this one's a little different than what we've been doing. It's asking how many liters. So we're still going to start with our formula, but now we're being asked for liters. So I need to get it out of the denominator. And this, by the way, is probably going to be the hardest. If there is a hard part to this, might be the hardest part of the calculations, is just getting your formula to where it's liters equals so that you can just plug everything in. So because it's in the denominator, it's dividing right now. I'm going to multiply by liters to cancel it out. Because this is an equation, these are equal, I'm going to have to do the same thing to the other side. So I'm going to multiply by liters on that side. But I still need to get liters by itself. I want liters equals. So how do I do that right now? If I'm multiplying by molarity, divide by molarity. Do the same thing on this side, divide by molarity. So what you get is liters equals moles divided by molarity. And we can just plug that in. We know our moles value was 2.11 moles. So if we can move that down, there we go. It is 2.11 moles of potassium permanganate. Molarity equals 1.66 molar. So to plug all of that in, I have 2.11 moles divided by 1.66 molar. Plug that into your calculators, and you should get 1.27 liters as your volume. And that is what most of your calculations are going to be like. The only other difference you might have is if you have to convert from grams to moles, and then all you have to do is use the molar mass from the periodic table, and then the rest of the calculations are the same. And that's it. You've got it.